Okay, here's our second installment of 4.1 looking at antiderivatives. So as a reminder, we're looking at what happens when we go backwards from a derivative. So instead of saying, here's the function, find the derivative, we're looking at a function and saying, what function has this function as its derivative? Okay, so the basic rules that we looked at yesterday are here on the screen. So we started with the integral of 0 dx. Okay, the integral of 0. And our question is, the derivative of what gives us 0? And the answer, of course, is a constant, right? Okay. The next one we ask ourselves, okay, the integral of k dx, where k is a constant. The derivative of what will give us a constant? Kx, that constant times x. And then we also have the plus c. What is that c? Okay, the constant of integration. The constant of integration. Okay, so that's what we use to show that there's a whole family of functions that could be the antiderivative because the derivative of a constant is 0. Okay, there's a couple others. We went through some other ideas with the antiderivative of 3x. And today we're going to take a look at how it's sometimes necessary to rewrite a function before taking the integral. But all the integrals we do are going to be based on these basic functions, or sorry, these basic formulas or rules right here. All right, so here we have 3 examples, and for each one what we're going to do is first rewrite it, then integrate it, and then write it in a simplified way. Okay, so I'm doing this in really slow baby steps for today. Obviously in the future you'll be able to do this much quicker and do some of the steps in your head without writing them all out. Okay, so here, number 1, our original integral is 1 over x cubed dx. Okay, we always have to have that dx with the integral so we know what variable it is we're integrating with respect to. Just like when we took a derivative, we always had to have the dx on bottom to know what variable are we taking the derivative with respect to. Okay, all right, so back to our problem here. Rewriting this, okay, I'm going to rewrite it as x to the negative 3 dx. So taking a look at our exponent, that turns it into our power rule, okay, and if you'll remember our power rule, the integral of x to the n dx, we kind of discovered that by trial and error yesterday. Do you remember what it is? So it'll be x to the n plus 1 over n plus 1. Perfect. Okay, so in this case, all right, once we integrate, we'll get n to the negative 3 plus 1. What's negative 3 plus 1? Negative 2 divided by n plus 1, negative 2 again on bottom. And then we always have to have our plus c, our constant of integration. Okay, and so if we write a final answer, okay, we can move the negative to the top and move the x to the bottom. We would get negative 1 over 2x squared plus c. There's our final answer. All right, that's pretty straightforward. Okay, most of the ones that we're rewriting here are polynomials of some sort. So this next one is similar. We want to rewrite it as a degree, but first of all, I'll write it the original one. Okay, integral of square root of x dx. How can we rewrite that with a exponent? You got it. Okay, x to the 1/2 dx. All right, now we follow our same rule from above. What's x to the 1/2 plus 1?
X to 3 over 2.
Yep, good. X to the 3/2 divided by 3/2. Okay, plus c. All right, so that's the sort of messy way, but correct. And then our last step, we'll simplify it. We'll flip the fraction from the bottom to the top. So we're left with 2x to the 3/2 over 3 plus c is our final answer. Okay. All right, the last one, we're going to take a look and use our constant multiple rule to factor out the 2. So we start out with integral of 2 sine x dx, and we know we can factor that 2 out in front of the integral so we don't have to deal with it, and just leave the sine x dx in the middle. And remember, we're asking ourselves, what function's derivative is positive sine x? Okay, negative cosine x. So what function's derivative is positive sine x? It's negative cosine x. And we're going to have to do a plus c at the end, and our 2 stays out front. So our 2 shows up in front of our answer here. Okay, so writing it in a final way here, negative 2 cosine x plus c will be our final answer. All right, any questions about that? All right, as a reminder, you can always check to make sure that you did the integral correctly by taking the derivative of your answer. And if you take the derivative of your answer, you should end back up with what you started with. And if you don't, something went wrong, okay? So you have to look at it again, okay? But you can always take a derivative of your answer to check. Okay? Not cheek, check. There we go. All right, excellent. Okay, we're going to do 3 more examples and then some practice, okay? So these are our basic ones. First of all, you should recognize that given the rules that we've looked at so far, we can integrate any simple polynomial function, okay? So this first one's pretty straightforward. The next 2, we see how we can rewrite and then integrate, still using the same basic rules, okay? So the first one, the integral of dx is the same as saying the integral of 1 dx. So 1 is a constant, all right? And we said before that the integral of a constant is just equal to that constant times x plus c. You got it. So if we write it in simple form, it's just x plus c. That's it. So the integral of dx is x plus c. Okay, that's 1. Number 2, we can apply our addition rule here. So the integral of x plus 2 dx. Notice there's parentheses to indicate that the dx applies to both the x and the 2. Okay, this is the same as saying the integral of x dx plus the integral of 2 dx. So we can break it apart in our head, make sure we understand, then integrate each part. So the integral of x dx is going to be our x to the n plus 1 over n plus 1. Okay, so in this case it will be x squared over 2 plus the integral of 2 dx will just be 2x. And then we can just put one constant of integration out front. Okay, technically you would have 1 here. You could have a constant there and a constant here. But they're both just constants. So in the end you could just find one constant and it's just a little bit less to write, a little bit cleaner. Okay. So that's your final integral for that one. And then the last one is just a couple more terms, okay? The integral of 3x to the 4th minus 5x squared plus x. And again, notice it's best form to use parentheses and then your dx to show that that dx applies to everything inside your parenthesis. All right, and then we can rewrite this as 3 separate integrals. I'm not going to do that again because that's what we did in the previous one, and I think it's pretty straightforward. So take a look and take each term one at a time, all right? So we know our general rule is the integral of x to the n is x to the n, dx is x to the n plus 1 over n plus 1. This is getting messy. I'm going to rewrite it. All right, integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. That's our general rule. Okay, so for each of our individuals here, the first one, there's a constant. That can just stay out front. And we're just dealing with x to the fourth. All right, so then our integral of x to the fourth by itself is over 5, right? X to the fifth over 5. All right, the next one, same thing. The 5 can just stay out front. All we're dealing with is x squared. The integral of x squared will be good, x cubed over 3. All right, and then the last one, we have no constant. We're just dealing with x. The integral of x is very good. All right, and then once again at the very end, we need a plus c. All right, I am going to simplify it just once more to get all the fractions together. 3x to the fifth over 5 minus 5x to the third over 3 plus x squared over 2 plus c. There's my final answer. All right, so with this toolkit, you can solve tons of different kinds of polynomial problems, okay? All right, so there are some cases when something doesn't look like a normal polynomial right after the bat, okay? You have to rewrite it first, and you should definitely plan on looking out for these, okay? This right now looks like you would have to use some kind of quotient rule, but remember, we don't have any kind of quotient rule yet for how to deal with rational integrands, okay? So what we want to do is instead rewrite this as a single polynomial, okay? So the first thing we'll look at is separating it into two fractions. So since there's only one term on the bottom, we can separate the terms on the top to x over square root of x dx plus integral of 1 over square root of x dx. Okay, and now we can rewrite those even simpler, right? X over square root of x, we just subtract the exponents, right? So x to the 1 minus x to the 1/2 gives us just x to the 1/2 dx. And then 1 over square root of x is the same as x to the negative 1/2 dx. Okay, so now this is straightforward. We can go back and use our same old rule. Okay, x to the integral of x to the n dx equals x to the n plus 1 over n plus 1. All right, so doing that for each of these, in this case, n is 1/2, so it's x to the 3/2 over 3/2. Okay, and then this is one place where it can get really tricky, right? You're adding to a negative. So negative 1/2 plus 1 is positive 1/2, and then it'll be over 1/2 plus c. Writing our final answer, flipping the fractions, we'll get 2x to the 3/2 over 3 plus 2x to the 1/2 plus c. Nice, beautiful final answer. It's important to note that in this case it would not be appropriate to integrate the top and integrate the bottom separately. Okay, you can't do that. You have to treat it all as one. So if you're not able to rearrange it and make it look like a polynomial like this, you can't solve it. Okay, and we'll learn some more techniques as we go on how to solve more complicated ones, but as of right now, if you can't turn it into a polynomial, too bad, just wait. Okay. All right, and there are some other situations, particularly involving trigonometric functions, where you just have to get creative, okay? So before, canceling out x's and grouping them is pretty straightforward. Sometimes it takes having a good memory to be able to solve these trig ones, because you have to remember the trig identities, all right? So here, if you ever see a cosine squared or a sine squared, and there's just a single sine or single cosine with it, one good trick is to try writing the square as two terms. So for example, integral of sine x over cosine squared x dx. Try rewriting this as 1 times sine x over cosine x times cosine x dx. Okay, now this is the same thing as what we said before, but now you can look and you can group 1 over cosine times sine over cosine. Okay, what is 1 over cosine equal to? 1 over cosine is secant, that's correct. So secant x times, what is sine over cosine? Tangent x dx. And now you look at it and you're like, wait, that looks familiar. The derivative of what gives me secant times tangent?
Tangent x.
Secant x.
Oh.
Secant x. All right, the derivative of secant x plus c will give me secant x times tangent x. Okay, but notice when we first looked at it over here, okay, it looks like weird fraction, we can't do anything with it, all right? We had to rewrite it first, and sometimes it just takes practice to know how to get creative and do that, okay?